Hi, everybody, and welcome to today is May 17th. Today we're there is a slight change in plan because of the fact that we didn't finish the problems from chapter 30. So what I'm thinking to do is actually move on to chapter 31 because the ideas for the RLC circuits are there too. So we need to finish the stuff that has to do with the AC circuit when we have them in the RLC circuit. And then we're going to do more problems from chapter 31 and 30 combined because they are actually related to one another, because one of them will have an RLC circuit with AC power supply, and the other one will have an RLC circuit with a DC supply, basically. So it's just a matter of what power do you have to use to power your circuit. So that's what we're going to be doing. So instead, we're going to go through chapter 31, introducing the ideas from chapter 31, namely the circuits that have to do with the resistors, capacitors, and inductors. And we're going to do them in lecture series, but it's not hard to actually think about how we're going to do them in parallel. As a matter of fact, we're going to give the general rules on how to handle circuits and AC circuits when you have everything combined together, okay? So that is chapter 31. So today is the 17th, which is a Monday. We're looking at ending chapter 31. Wednesday, when we meet next time, we're going to dedicate it solely to problems, which is the 19th. Then Monday, week from today, we're going to introduce chapter 32, okay? Chapter 32 deals with the electromagnetic waves. Basically, we take all of Maxwell's equations and solve them. And we're going to solve them in something called free space. Namely, there are no charges in there and no currents. Okay. Once we do that, we have the solution, which is the so-called electromagnetic waves. And those electromagnetic waves, basically, they give us all kinds of things. One of the main things that we're going to be introducing there is the Poynting vector. And it is related to those expressions I was telling you guys about from when we did the capacitor. We found the current, the electric field amounts to an amount of energy density, which is 1/2 of epsilon times E squared. And we also found the fact that not too long ago, actually from chapter 30, the fact that the magnetic field also, when you have a magnetic field in a region of space trapped, it amounts to an energy density, namely energy per unit volume, of 1/2 of B squared divided by mu naught. And combining this two, because then at that point we'll be dealing with the electromagnetic field, which is a combination of the electric field and the magnetic field, we'll find an expression for the energy in general when you have waves traveling in empty space by themselves, okay? And that is going to be expressed in terms of the Poynting vector. Poynting vector is the intensity of the waves, actually, and that intensity is related to this energies that we've been talking about. So that's going to be the end of this course. So I'm hoping by Monday we will cover everything that there is need to be covered. Now, Monday the 31st, there is no class on Monday the 31st because it's a holiday. So we're going to see how we're going to adjust the stuff so that we can do enough applications from chapter 32. Chapter 32 applications are kind of light a little bit compared to these things, but they will be there. Okay, so we still have at least the 26th and probably also June 2nd where we can meet, and maybe one of them has to be, we will just basically discuss the overall plan and things like that, and we'll be done with the class. Okay, so let's follow up with what I was saying. Any questions before I jump into chapter 31? Nope. So let's get going. So first of all, we're going to go through the AC circuit, AC current, I should say. And this is stemming from the fact that Faraday's law, excuse me, gives me the flux of the magnetic field being the area of the field times the magnetic field. So it's really the sum of dA times B summed over an area in here, okay? this area may not be closed. Here is the design for this circuit, okay? So here is what we do. We have a magnet in here, permanent magnet. I'm doing it this way, but it could have been done the other way around. So you have a north pole on one side in here, and you have the south pole in this side. So what's going on in here, the magnetic field obviously will be pointing this way, in this region of space, okay, between them. Now, you take in this case and you bring a loop. I'm going to design it with one loop in mind, but obviously you can have, so we need to do something about this loop. It doesn't look too good. We need to tilt it a little. So I'm going to tilt the loop. And from the other side, we're going to basically have it spin, okay? So you have a wire in here. This is a conducting wire. And it's basically allowed to spin with a frequency omega. You come in this side and here, and usually you have brushes attached to this ones, just like this shape. Let me stop sharing so that to show you how it looks like. This is actually a motor, and using motor is actually a reverse engine. If you see on this side in here, this it looks like a this piece in here that is standing out. That is actually the brush, and it's on both sides, okay? So when I spin this one on one side or the other, the brush keeps on contact, and there is a gap in here, and that gap will break it so that the current will flip on this side. So basically, here is the deal. So on at some point, one side of this circuit will be in contact, and the other the other side will be in contact. That's basically what it is. So at this point in here, take this one and connect it to a resistor, for example, or light bulb, or whatever you want to do.
You're not sharing anymore.
I'm not sharing. Sorry. Thank you. Okay. So in this case, you connect it in here, and it's going to be connected to a resistor. So those two brushes, basically, they spin, and at some point, this one will be on contact, and this other leg will be on the other contact, and vice versa, because there is a gap in there. Okay, so the engineering is quite interesting in here. But the point being is the following: you have an area in here, A, that is fixed, constant, and you have a magnetic field in here that is fixed. And the angle between them is the only thing that changes. So the angle between them, phi, changes at the rate of omega t, depending on this omega. So what happened in here, the flux is then easy to do. The flux of the magnetic field will simply become phi b is going to be just b times a times cosine of the angle between them. Okay? And that is time dependent. So now, if I want to find the EMF produced by this battery, by this in here in this circuit, because there will be a current now flowing through the loop, okay? Because I closed it with the resistance. If I don't close it, then there will be an EMF, and the EMF is given by Faraday's law. So the EMF in this case is given to minus the derivative of phi b with respect to time, and that is the derivative of a cosine is just a negative sign. And that takes care of all the signs and everything. So this is basically what you end up with. So this current is an alternating current. So the current is an AC current. AC stands for an alternating current, as opposed to a steady current, which is a DC current, alternating current. Okay. So the A stands for an AC current, as opposed to DC. DC stands for a direct current. Okay, so we have a way now of finding a current that changes with time, and it changes at the rate. So this is basically what the current is. So this is one period, T. During the one period T, we have the cycle. Obviously, this is repeating and so on and so forth. So this is the period T in such a way that this current changes with time, and this cosine function. The cosine and the sine are the same. So sometimes I use a cosine, sometimes I use a sine. There's a 90-degree phase between them, because the sine of omega t is the same as a cosine of omega t plus, what is it? Minus pi over 2. okay? Because in this case, cos is 0 and plus sin, and that is the same thing. So this is trig identity. Trig identity says that cosine of any angle, alpha, is the same as the sine of the same alpha plus pi over 2. Okay? So it's the same thing. Okay? So move the 90. So in other words, this is what that means. Shift the origin from here by 90 degrees. Move it by 90 degrees, by pi over 2. Okay? By quarter period, because this is time actually, t now. So by actually t over 4. Okay? Move it by t over 4, and you have a cosine, because actually this is a cosine function. And this is the period for it. Remember, t is equal to 2 pi over times frequency, okay? And the expression here has, or omega times t is equal to 1. Omega is equal to pi. Omega t, no, that's wrong, t is equal to 2 pi over omega, I'm sorry, okay? Which is equal to 1 over f. So omega t is equal to 2 pi. So basically in this expression here, when you shift it by t over 4, so what you have shifted it actually in time is omega t over 4, and omega t is actually equal to 2 pi over 4, and that is pi over 2. So in angle, in phase, you have moved it by, yes, in time you have moved it by t over 4, but in phase, you have to multiply by omega to find how much angle you have added or subtracted, and in this case, just by pi over 2, okay? So in other words, the sine is just shifted cosine. So my point in here is, we can use cosine, we can use sine, it's just a matter of choosing the clock when to click it. If you wave t over 4, now the sine becomes a cosine. For example, in the United States, they use the frequency f in the United States is equal to 50 Hertz. Is it 50 Hertz? Did I get my numbers correct now? Or is it 60 Hertz? Oh man. One of them uses 50 Hertz, the other one 60 Hertz. I think the rest of the world uses 50 Hertz. Yeah, the United States actually uses, yeah, it's 60 Hertz, sorry. Okay, so that's how much it's used in here in the United States. Again, it's just the how often basically this thing spins. So if you are in the Hoover Dam and you're trying to build a power supply company, the power supply, that's what you do actually. Make sure it spins at that rate, okay? And that is the frequency omega of the signal. So the signal of the United States has this frequency. And from here, you can find what omega is. Omega is 2 pi f, and that is 120 pi, okay? Radians per second. And from here, if you're interested, how much the actual period of this is, the actual period in the United States, t, is equal to 1 over f, which is 1 over 60. Okay, that means it repeats 1 over 60 times. Basically, it goes back and forth. So in other words, how long do you have to wait? You have to wait a quarter of that time. Very insignificant, very small. Anyway, so this is the AC power supply for the signal. So assume from now on that we have an AC signal somewhere. We have this is the symbol for the source. This is an AC power source. In the United States, the voltage actually, and we're going to talk about the RMS, the root mean square, very shortly, but in the United States, the voltage RMS is 120 volts. And we need this number for later on, okay, to work with it. And I'm going to tell you exactly what the RMS stands for. So here is a battery, basically, how it's represented now. So if you see this element in a circuit, that means the plug. That means the power supply, okay? And usually there is a voltage V across it in here, how much it is. So in the United States, actually, it's going to be either an RMS or V max, one of the two. V max in the United States is 170 volts, and the RMS, the root mean square, or the effective voltage, is 120 volts, whichever way you want to define it. And we're going to talk about this once again. Because the signal is actually cosine or sine function. Its maximum value is this much, and its minimum value is the negative value. That's it. So you need the amplitude of the signal. So that is basically how we're going to represent this thing. So here is the deal. We have an RLC circuit in an AC environment. So this is how the circuit looks like now. We have a resistor. We have an inductor. And we have a capacitor. And they are all connected to a power supply. That is an AC power supply. Usually for safety, we're going to check this thing that's equal to 0. Switch S is closed. And the voltage, I'm going to call it V naught, which stands for V max. Instead of writing V max and take forever to write this one, I'm going to call it V naught. Okay. And the frequency is some frequency, which I'm going to call it also. I don't like this V naught because we will have an omega naught in here in the circuit, and we will have its own omega in here. So this is the omega of the circuit. So we're going to call it in this case, since it's a power supply, I'm going to call it. We have 3 omegas. So hopefully you guys will keep tab of your. So let's leave V naught in here. I cannot call this omega as omega naught because there is an omega naught in the circuit, and you will see that omega naught is 1 over square root of LC. So that is what we're going to call omega naught. We're going to also have an omega in the circuit, and that omega is going to be 1 over LC minus R over, what is it? 2L squared. Okay, there is also another omega in here, and there is actually an omega to the circuit now. So this is an omega coming from the problem itself. This is omega coming from the chapter 30 omega that you guys have seen, because now when the circuit is it's this expression, okay, which is the time coefficient of that factor, and that is the actual frequency of the signal, and this is the natural frequency of the signal without the resistor. Okay. And there is another omega now that I cannot call omega, but I'm going to probably call it omega prime now. Okay, this is omega prime coming from the power supply. This is the first 50 hertz, if you like, or 60 pi, 120 pi. So that is the signal that is giving you your circuit. So there is an additional omega now. So hopefully, so this is from the power supply. This is the actual frequency. Actual, there is only one L in here, of an RLC circuit, and this is the natural frequency. So a bunch of, we call them frequencies, but they are angular frequencies, okay? So we have a bunch of omegas in the circuit in here from the get-go. You have 3 of them. One that is actually the power supply. And the other 2 have to do with your own circuits. How much capacitance you bring and how much resistor you bring. And so let's keep some numbers in here, okay? Let's do some numbers in here because it really helps to visualize things with numbers. I'm going to take an L to be 470 millihenry, okay, which is a big value. I'm going to take a capacitors to be about, let's say, 10 microfarads. From here, I'm going to have omega already not equal to 1 over square root of LC, and that is equal to, let me get the calculator here. Hopefully you guys are writing these things. You're not relying on me only. Oh, I don't have my calculator on. Did anybody do the numbers? Yes, no? So what I said in here is I have square root of open parentheses 1 over open parentheses. What am I dividing? First of all, 0.47 times, did I take 6 or did I take 2? I forgot how much number I put in there. 10 microfarads. That's 10 to the negative 5, okay? Farads. And close the last parentheses and enter. So it's 461 hertz, 41,661 radians per second. You have to be careful now. When you're doing problems like this one, you have to be careful in here. This is omega, not frequency. So when you're given frequency, you have to divide this number by 2 pi. So if I really want to have the frequency in here and talk in terms of frequency, which is hertz, I have to take this number and divide it by 2 pi. So this is important insight into what's going on. So this is about 73.4 hertz, okay? Where is my, and I lost the, trying to find where my share is here. So omega naught, first of all, is 461 radians per second. That is the value that we need. But if you're curious trying to find the natural frequency in hertz, it's going to be 73.4 hertz. Okay, so this is the natural of this RLC circuit. If I give you R, and I have to be careful now with an R, I have to really choose it so that this oscillates. So if I take this number and square it, so let's take an R in here, which is a typical value in here, about 100 ohms, okay? And let's see what that does for me. So R over, what is it, square root of, open parentheses. So I'm trying to find the omega, I'm trying to find this value in here, the actual oscillation frequency in this circuit in here. So it's going to be this number minus open parentheses 100 divided by 2 times 0.47, close the parentheses, close the second parenthesis, and square this number because it has to be squared, and close the parentheses and take the entire square. It turns out that this frequency omega is 448.8 or 449 radians per second. So it's slightly less than the actual natural frequency, and it is because it's square root of something, omega naught squared minus something squared. So it has to be less, okay? And if you're curious trying to find it, how many hertz that is?
I have a question.
Yes.
What do you divide R by? Like you divided the 100 omega by a number. Could you repeat what number was?
Oh, to find the, I divided the R by 2L.
Okay, thank you.
Okay, the L I took as a 0.47 Henry. I took 470 millihenry. Okay, I'm just trying to throw in numbers so that we have a visual of these things, because sometimes we talk about symbols and then you lose track of what they mean. Okay, so it's really very helpful sometimes to get things into perspective in here. Okay,
Thank you.
no problem. So it's 2 pi. So the frequency is always related to omega by dividing by 2 pi. So this turned out to be, the F in this case is 71.4 hertz. And it is expected to be less because of the square root, remember? Square root of that minus this number. So again, these are typical numbers, you find them in the circuits, okay? 10 microfarads is something that you find. I don't know how many farads is this one in here. This is actually 22 microfarads. I don't know if you can see it or not, but this is 22 microfarads. So these are typical numbers that you can work with them. So this is now something. Now add to it our circuit frequency, which is 60 hertz. Okay. And if I'm doing this, plugging this into the wall, F prime is actually 60 hertz. That is coming from the wall. So this is the wall. You understand now that I have 3 frequencies to work with? One of them is the natural frequency. We're going to find out how important that is. It's going to play a major role in the circuit. And this is the actual frequency that we can actually monkey around just with changing things. If you don't want to mess around with an L and C, you can play actually with an R to change this number. Okay? You can make this number as, you can make a 0 actually. Because if you play around with R in here, you can make this whole thing 0. You can make this whole thing go away. Okay? So there are things that you can do in here, but there is also F prime in here that is coming from the wall. So that is basically this circuit. So at t equal to 0, we close the circuit. And at that time, I is equal to 0 in the circuit. Okay? There is no charge in here. There is nothing. Q is equal to 0 also. Okay? Here is the trouble with this circuit. And now I'm going to write Kirchhoff's rules for it. So I'm going to start from this point, and I'm going to take this signal V, or the EMF, to be actually V naught cosine instead of a sine, okay? Cosine of this omega prime t, okay? So that is my signal. So if I start from any point, I'm going to start from here, follow this one is going to be Ri at some later time. That is the drop in voltage. The drop in voltage in here, L di over dt. We know how to do that. The voltage in here is Q over C. And now it's actually a rising potential by this amount. Okay? So if I write this expression, this is how it looks like. Ri plus L di over dt plus Q over C is equal or minus, because there is a rise. I already moved it to the other side, and cosine of omega prime t is equal to 0. So this is the expression that we have to deal with. Doesn't look too good at all. Let me write it down a little bit more friendlier. I'm going to write L. First of all, I'm going to write it in terms of Q. Remember that I is equal to dq over dt. So this is just the second derivative. That means di over dt is just the second derivative of Q with respect to time. And now the expression looks like this. D squared of Q divided by time. When I divide the entire expression by L plus R divided by 2L times 2. I already did that step, okay? Times I, and I is dq over dt plus 1 over LC times Q is equal to V naught over L times the cosine of omega prime t. Again, I'm going to call this guy lambda. Did we call it lambda? No, we called it. Did we call it lambda, or I forgot what we called it in this class. I think we called it something else. Okay, I'm looking at my notes, okay? No, we called it B. Okay, we called it, no, actually that's B for the mechanics part of it. Mechanics part of it. Tau, we called it tau. Okay, so let's stick with the same notation in there, okay? So we call it tau. So this number is called tau. This is actually omega naught squared. And this is by itself now. So let's look at the circuit now and see exactly at least the expression, how it looks written in this format. Plus 2 tau, the first derivative of Q with respect to time, plus omega naught squared. Q is equal to V naught over L times cosine of omega prime t. This doesn't look too good at all. This is actually a very bad looking equation. It's actually of the second order. Coefficients are constant because tau is equal to R over 2L, and omega naught is what I defined up there. And this V naught over L is another thing in there. So this doesn't look too friendly at all. Let me tell you what this equation, how we're going to proceed about it. There are two solutions. there is a transient solution, and this transient solution will decay as exponential of negative tau t. Okay? Sometimes you will find it in the expressions, and I think I made a mistake. We were choosing this tau. This is actually in other literature and a lot of places is used lambda for it, okay? So if you see lambda or you see me referring to it as lambda, it's the damping factor actually. This is the damping factor, and it is actually proportional to the resistance. The more resistance you have, the more damping you will have. In either case, whether it's heavily damped or critically damped or even an oscillation, but that oscillation is with damping. On all scenarios, this will decay to zero. This will go to zero. That's why it's called the transient. It decays with time. So if you wait long enough, it's going to decay. And tau is the one that tells you how long it's going to take for this one to decay. To go back into my example, tau that we calculated in the circuit was equal to R over 2L, which is this number. Where is R over 2? We didn't calculate R over 2L. So I really need to calculate R over 2L, which is 100 divided by 2 times 0.47. Okay. It's 106, 1 over second. Okay. So that is actually the inverse of that is time. So if I'm going to invert this number, so it's going to decay in about 0.009 seconds or 9 thousandths of a second. So after 9 thousandths of a second, this number goes to zero, practically. Because tau for this numbers that I chose in here is equal to 106.4, basically, 1 over seconds. The unit for it is 1 over second. So the inverse of that is the time characteristic, okay? And the time characteristic in here is going to be 0.0094, which is roughly 9 times 10 to the power 3 seconds. So if you wait this long, this basically less than a second, this thing will go to zero. So that's why the transient usually is not good. You don't focus on it. It's going to decay exponentially. And what determines it is that resistor, really, R. And the ratio of R and L is the one that dictates how fast this will go to zero. So in this case, it's going to go fast to zero. There is another solution which is called the steady state. And the steady state is the one of interest to us, because you have here an external signal. By the way to find this one is easy. All you have to do is make the second half equal to zero. So it's going to be the same equation that we did in chapter 30, which is this equation. And this, we have seen it, that it leads to one of those three cases, either overly damped, or critically damped, or damped with oscillations. In either case, this is the time with which you have to wait for this thing to go to zero, practically, okay? If you think this is too short of a time, wait about hundredths of a second, or a tenth of a second, or a second. Second is plenty time in here. 1,000 times these frequencies were gone, okay? So it's gone. So basically, this is too much in here for it. So it's going to be gone for the most part, okay? So in either case, this is a factor that is leading in front of all of the other terms. So it's going to cancel this equation. Now we're going to look for a special solution. And the special solution will have the same frequency as the driving force. This is called the driving force. In other words, your circuit is an RLC circuit, and it's being managed by an external force that oscillates with the frequency omega prime. So omega prime will dictate how fast the circuit is going to go back and forth, and it's this voltage that you're going to have. So there is a steady state. In math books, they call it the special solution. okay? How do you find it? By making an assumption. And that assumption is that Q is somewhat some Q naught times this cosine function, okay? Obviously, when you take the first derivative of the cosine is going to be a sine. And when you take the second derivative of the cosine, if the cosine is going to be also a negative cosine, so this term will have a cosine in it, and this term will have a cosine in it, and this term will have a sine on it. It's very hard to do that, even with check function. It takes several pages to actually complete the calculation. That is step one. Option two, using complex numbers. Complex numbers, you make the cosine in here as part of a real, part of a big complex number, which is the using Euler formula, okay? And then you make a solution that is actually an exponential, and this will be an exponential, and this will be an exponential, and this will be an exponential, because the derivative of an exponential is an exponential. And that is easy, actually. That is actually the preferred way of doing physics. So you have choice one, which involves check functions themselves, like this one, and manipulating it and getting to the answer to find Q, to find the special solution. Second method is complex numbers. If you use complex numbers, it's actually a lot faster, but you get also the same answer. The third method is the Phasors method. And we're going to introduce today the Phasors method, okay? To use the Phasors method to find the solution to this equation, okay? The fourth way is actually to change the circuit based on the solution in here and actually use Kirchhoff's rule, modified, okay? Modified Kirchhoff's rules. We're going to define what I'm talking about in here, okay? So, since the book uses Phasors method, I'm going to use the Phasors method, and hopefully you guys will understand what that means, okay? So, because Q is going to be a cosine, so the current is going to be of some sine of some sort. So I'm going to make the current I to be some I naught, which I don't know and I need to find, times the sine of omega prime t, okay? If the current is this way, it's clearly the voltage across the resistor will be simply R times I, and that is R times I naught. So again, I need to find I naught, okay? We need to find this current because we don't know it, okay? Or what I mean by I naught, let me remove the naught in here because I mean just the amplitude of the current, that's all. I mean, because the current has two components in it. It has an amplitude and it has a frequency, and I'm assuming the frequency is that of the driving force. So the frequency, we're going to fix it because the whole purpose in here is to find a solution. That is the steady state. And the steady state is being dictated by the voltage, the external voltage. So it better have its own frequency. Not only that, but I expect also this current to be proportional to this V naught, to be proportional to this external battery, to be proportional to the plug, how much voltage is coming from the wall. Because if I unplug it, there should be no current in the circuit. If I move it from the wall, there cannot be any current, so the I should go to zero with it. So this I in here better be proportional to, I don't know how much, but basically I expect it to be proportional to V naught. So we need to find that assertion. Because the assumption is, if I unplug the wall, the whole device from the wall, there cannot be any current in the circuit. That is the whole thing. So with it, when this is unplugged, this should go to zero immediately, okay? So that is the thing with it. So we need to find a solution that behaves this way. So that is the voltage across the resistor. The voltage across the resistor is just Ri times just in this case, the sine of omega prime t, okay? So that's easy. How about what happened to the voltage across the inductor? The voltage across the inductor is going to be L times the derivative of the voltage across the current. So in this case, I know how to take derivatives for sine, and that is going to be omega prime times L times I times the derivative of a sine again is cosine, correct? Okay, very good. So I already mentioned the fact that there is this cosine and the sine are within 90 degrees of the same one another. Okay, if you shift the cosine one way or the other, this is true. So the fact that I found the cosine in here, when taking the derivative of the sine, I'm going to convert it back into a sine, but add to it a pi over 2. So add to it a pi over 2. So this will become omega prime Li times a sine of omega prime t, because I want to keep it in the same spirit as the current, but I need to add to it pi over 2. So it looks like the voltage across the inductor is the same voltage across the resistor, but shifted by 90 degrees upward. Okay? In other words, the voltage across the inductor is ahead of the current by 90 degrees. Here is, this one is sine omega t prime, the other one is sine omega t prime t plus 90 degrees. That's what pi over 2 stands for. Okay. Now I need to do the same thing to find the voltage across the capacitor. The voltage across the capacitor is Q over C. And Q, remember, is the integral of the current. Q is the integral of the current because I is equal to dq over dt. So I really need to integrate this sign to see it, the expression for it. So the integral of sine is 1 over omega prime times cosine with a negative sign. Okay, so it's going to be negative I over omega c times a cosine omega prime c, I'm sorry, omega prime t. Does everybody agree with this expression up to this point? Because here is a current, the current actually is here, I sine omega prime t. So if I want to find its integral, this better be negative 1 over omega prime times I times a cosine of omega prime t. Does this make sense to you guys? And I need the negative sign. It's needed there. It's not an option because when I take the derivative of the cosine, it's going to give me a negative to cancel that negative. And then I will put an omega prime to cancel that omega prime, and the derivative and the cosine becomes a sine. Does this make sense to everybody? Okay, very good. So now everything looks good, except that I have a cosine again. Okay. There is another identity that I need to use in here. Actually, I can't use this one because I need to make sure that it's a sine. And if I use this one plus pi over 2, that is actually going to give me still a negative sign in here, and I don't like that. So there is another identity in here. All I have to do is subtract a pi over 2. Let me show you what that means, okay? So first of all, there is a I over omega prime c times a sine of omega prime t minus pi over 2. Because sine, cosine is 0, plus cosine or minus cosine sine, and that is going to be correct. So actually, this is another trig identity that I'm going to use in here. So cosine of alpha is the same thing, or negative cosine of alpha is the same thing as a sine of alpha minus pi over 2. Okay, so that is another trig identity. So if you're not fresh on your trig identity, this is something very, very important that you have to do. As a matter of fact, as an engineering student, as an engineer, as a physicist, this is one of the things that you should know. Okay, this is the things that you should not really look them up. I mean, you may probably look up maybe your birthday or your social security number, but these things you should remember them by heart. Good. Promise you do that, guys? Free up your brain from your, okay, good. Free up your brain from your birthday and your social security numbers, but put them instead, these things, because they are coming handy. You need them a lot. Okay. So this is another identity. So I'm going to plug it in here. So this is how it looks like now, the voltage across the capacitor. So the voltage across the capacitor, if I take advantage of that one. So it's I over omega prime C times a sine, again, of omega prime T minus pi over 2. So it looks like the capacitor, the voltage across the capacitor is lagging by pi over 2, whereas the other one was ahead, compared to the current. So this is what I'm going to say in here. The voltage, these remarks are extremely important. If we're doing a lab in class, this will be actually very, very important, because you have to recognize, you will have all kinds of, you will have so many basically leads coming from the probe to the different components of the circuit, and each one of them has a plot, and you're supposed to find which one is ahead, which one is behind, and you will see the current, and from there you determine which one is the voltage across the capacitor, which one is the voltage across the inductor, which one is the voltage across the resistor, which one is the overall voltage, and based on that you're going to make decisions. So in a voltage across the capacitor lags behind the current by 90 degrees. So across the inductor is ahead, across the resistor it's not, it's in sync. VR is equal to Ri sine omega prime T. So the voltage across the resistor is in sync with the current. In other words, it's not ahead, it's not behind. It's just add 0 to it if you want to. Okay, it's the same thing. So hopefully you guys you saw where where these things are coming from. The fact that the voltage across the resistor, the inductor, is ahead is because of the fact that you're taking a derivative, and when you take a derivative of the sine, it becomes a cosine, and the cosine is the same as a sine except added to it 90 degrees. The fact that the voltage across the capacitor is actually the charge over the capacitance. When you take the charge, you have to integrate that expression. When you integrate it, you're going to put a negative sign, and then you're going to change the sine to a cosine. So now if you want to convert that back to a sine, you have to subtract from it pi over 2. When you do that, that means the voltage across the capacitor is actually lags behind by 90 degrees, and here it is. In the case of the resistor, you don't do anything, you just multiply by R. That's why it stays the same, they stay in sync. You don't add or you don't subtract. So the signals look identical in here. So this is how I'm going to represent it, okay? And please pay attention to the representation, because sometimes it differs from book to book, from place to place, okay? So I'm going to pick up a big circle in here just to represent my Control Z. I want it to be a circle. I don't want it to be an oval. Okay, so in here, in this X direction, and this is the Y direction. Let me go back into my shape and see if I can center it a little bit. By the way, in the lab, you're going to be drawing something like this, okay? So you have to pay attention to how this works, okay? So let me draw the voltage across the resistor, across the current. I mean, which is the current, which is the resistor, really, because they're in sync. So it's going to be a vector. And depending on how much big R is, it's going to be something like this. So this is VR, and VR is Ri, okay? I'm going to draw the voltage across the inductor, and the inductor, if you guys remember, is ahead by 90 degrees. So I'm going to draw it along the y-axis, and I'm going to multiply it by omega prime L. Okay, so that depends on that value. Okay, so I can't really, I wouldn't know upfront how much its value is. So let's say, for example, this is how much it is. Okay, why did I draw it a circle? Let's draw it smaller than that then. Okay, so this value in here is how much? It's omega prime L times I. I'm going to draw the last one in component in here, and that is going to be behind by 90 degrees, lagging behind the inductor, the resistor, the current, which is where the voltage across the resistor is. So I'm going to draw an arrow again. That depends also on C, how much C is, and so on and so forth. And so let's assume that this is this number, and it's lagging behind. So it's along the y-axis, except behind the other one. And its value is going to be equal to I over omega prime C. So this is the three voltages, basically. The three of them, clearly, when I add them up, are going to be the voltage across, what is this circuit? Did I write it? Did I ever write it? They're going to be the voltage across the entire wire, okay? Which is just V naught. So when I add them up, they have to be better V naught. So I am going to add, what I'm going to add three vectors now. What happened to omega prime T? Well, we took it to be 0, okay? And we draw vectors from that point on. In other words, this is the cosine. I'm sorry, did I draw it in a cosine? This whole thing needs to be flipped, but that's fine, okay? Remember, we shift the cosine at will, okay? By 90 degrees. Technically, this should be a sine and everything should be flipped. Hopefully, you guys are not thrown away off by this representation. So in other words, I just took the original of time so that it's 90 degrees shifted from the other ones, that's all. But now, the main thing in here is that you have to draw these vectors in here. Obviously, I need to find the difference between the green vector and the blue vector. If the green vector is leading, in this case, the circuit is called an inductive circuit. If omega prime L is, obviously the I is the same everywhere, so I don't care about that. So it's if omega prime over L times L is bigger than omega prime C, in this case, we have what is called an inductive circuit. Now, there is another possibility when omega prime times L is less than omega prime C, and in this case, we have a capacitive circuit. There is a possibility, actually, when both of them are equal to one another. I'm sorry, 1 over, what am I talking about? Is equal to 1 over omega prime C. Okay, don't forget, it's 1 over, not the exact value. So that is, in this case, I can find what omega prime is. Actually, omega prime squared is equal to 1 over LC, which is omega naught squared. So in this case, when omega prime is exactly equal to omega naught, we have what is known as resonance. And in this case, both of them cancel, because this one cancels the other one. And the only thing that is left is the resistance. So actually, this is a resistor, not a resistor. This is resonance, period. Yeah, the only thing that's going to remain in this case is the resistance, okay? So as a matter of fact, we have names for these values. I'm going to call XL as being omega prime L. This is the impedance of the capacitor, the inductors, or the inductor. I'm going to call XC as being 1 over omega prime C as being the impedance of the capacitor. And I'm going to call XR, which is just R. This is the impedance of the resistor, okay? So we have new quantities now in play when it comes to AC circuits. The impedance. And the units for them are, the unit for XL is the same units for the XC. Remember, XC has 1 over. Is the same units for R, and that is the ohm. They are all in ohms, like a resistance, but they are actually not in the sense that they are resistance. That's basically the same units. So I can say how many ohms is the inductor impedance, and so on and so forth. Now I'm going to define a new quantity called the oh, I'm sorry, that's not the reactance. I call it something else, which they are the same thing. Okay, so this is called actually the reactance in the book. This is called the reactance. This is called the reactance. I'm sorry about that. Okay. The impedance itself is actually the sum of all of the reactances. Obviously, when I add up these two vectors, clearly the sum of these two vectors is some vector in here. Okay, so I'm going to draw the arrow. In here, it looks like the green arrow is green is more than the blue, so it's probably the difference between them is going to be this number somewhere in here. Okay. Now the actual resistance is the sum of these two vectors. So basically, add this vector to the red one, and now you have the actual sum. So what you do normally when you're adding vectors, you go from the tip of one to the other one, and you draw the second vector, and that is how the actual voltage across the entire circuit is. So this is V as a whole thing. So this is the special V. This is actually the response to the circuit, okay? And this is by definition is equal to ZI. So the voltage across the resistor, the entire circuit, is going to be by definition the impedance times the current. This is the circuit impedance. And it has the same units as, so Z has the same units as XL, has the same units as XC, has the same units as R, and all of them are in ohms. Because it's a voltage divided by current, and that is, it looks like it's Ohm's law, okay? Everything looks like it's an Ohm's law, because even the current, the voltage across the inductor is going to be, what is the voltage across the inductor here? It's this number, which is XL times cosine, and cosine can be only +1 or -1 at most, and it's anywhere in between them, okay? So it looks like it's an Ohm's law, where this is the resistance times the current. So the resistance has to be in ohm. So this is what I'm calling the impedance, the reactance in this case, from the voltage, the reactance of the inductor, okay? Except that it's shifted a little by 90 degrees. If I do the same analysis, this number, which is XC, looks like a resistor again, times your current, and the current is shifted a little, not the same current as we started with. There is a reactance of the resistance is exactly the same old resistance, because the current is not shifted and the current is multiplying it. So everything looks the same. So now the overall value, by definition, is just the impedance times the current. Okay. So now, if I want to, this is how the actual voltage is across the entire circuit. It looks like it's the impedance times I times a sine of omega t plus phi, because I have to allow for that to see how fast is, how shifted it is. This is going to be, it's clearly not in sync with it. This is phi. For the green line, it's 90 degrees. For the other one, it's -90 degrees. For this one, it's this angle. And this angle is clearly the ratio, or the tangent of this angle is the ratio of the difference between this one and this one divided by R from this right angle triangle. So the tangent of phi is actually equal to XL minus XC divided by R. You can clearly see from the geometry, this is this whole thing is XL times I. And this whole thing is XC times I. And this whole thing is XR times I, or R times I. So if I divide this, the opposite divided by the adjacent, that is actually the tangent, okay? And that is exactly how we found this phase shift. If you want to plug in the numbers, well, this is omega prime L minus 1 over omega prime C divided by R. Then you know how shifted it is. The length of this vector is clearly equal to, by the Pythagorean theorem, R squared plus this difference squared. So in other words, the impedance, I can find it too for this circuit. Z is the square root of R squared, that is the x-axis, and the y-axis is XL squared, XL minus XC squared. Or, if you want to write it more explicitly, as the square root of R squared plus omega prime L minus 1 over omega prime C, the whole thing squared under the square root. So we found actually the special solution by construction. So the special solution we found, and this is the steady state. As a matter of fact, now we can write it in its full-fledged form if you want to. I know I have a sine in here, and I started with a cosine, which is fine. I can convert the cosine to a sine if I want to by shifting 9 degrees. But the point being in here, this signal is similar in frequency, and it's in amplitude similar to the original signal. So let's do things in here. Let's get things done in here, okay? So here is, if we go back into the circuit, so what we have in here, okay? We have the voltage across the capacitor, the overall circuit, which is this one times the current, okay? So it's going to be square root of R squared plus omega prime L minus 1 over omega prime C, the whole thing squared, times the current, and this must be equal to the actual voltage across the capacitor, okay? Across the EMF, okay? Across the EMF. The sine and the cosines, they're just the time-dependent factors at this point, and I'm not to worry about them because they are going to be ignored. They're going to be canceled, actually, okay? And I can change my signal from the cosine to a sine back to a sine. So at any rate, we found an expression. Oh, no, I'm sorry. There is a 90-degree shift in here that I need to include back in the phase, okay? So that needs to be included back in the phase. From here, we have the value of the current, the amplitude of the current. R squared plus omega prime minus 1 over omega prime C, the whole thing squared and the square root, okay? And that's exactly how we thought we should have the result for the current. The current had better be proportional to V naught. In other words, if I turn off V naught or I plug my device, the current should be 0. And indeed, that's what we thought in the beginning need to happen. Because if I unplug my device, the current better go to 0. So we found the current, we found the phase, we found everything in here that we need to find. So we have a full analysis of the problem without doing really a lot of work, honestly, because the only thing that we did was trying to understand this diagram in here, okay? Trying to see, based on the arguments that we did in here, what's going on in terms of my current and my circuit and how things are moving left and right with respect to one another, okay? So this is, in terms of problems, this is the expression that you will need in here to remember, or actually come back and refer to. And the other one that is important is the phase shift. In other words, how to find the impedance in here. Okay, so let's see how we're going to do circuits now, based on these ideas. If you're given a complicated circuit that has a resistor in it, not necessarily this, okay, not the necessarily in parallel things like it has an inductor and it has a capacitor. The first thing you do in here is change all of your, and then they give you an external frequency. Let's say if it's omega prime. Then you change every single component from a resistor to a black box called XR, okay, which is just R in this case. You take this one and you convert it into a black box as far as you're concerned, and it's called an XL. Okay, you take this one and you convert it to another black box that is called an XC, where XL is omega prime L, and where XC is going to be 1 over omega prime C, and where XR is just the R itself. And then you redraw the shape based on the new diagram and use Kirchhoff's rules after that. And use Kirchhoff's rules. That's it. So in other words, this is how the circuit looks like now, the same circuit that we draw up there. So this will become like a resistor R. This becomes like an XL. This becomes like my XC. For convenience, we usually don't write XR in here because of the fact that it's the same thing. Your switch stays the same. This becomes your power supply, okay? You could keep it like this, but don't write anything but just this number in here. And that's it. So now if you want to apply Kirchhoff's rule, Kirchhoff's rule, you have a drop in voltage, which is Ri. You have a drop in voltage, which is XLI. You have a drop in voltage, which is XCL. And this is shifted by 90 degrees. And this is shifted down by 90 degrees, okay? So you can't just add them up like that, okay? You have to account for the fact that they are shifted. The impedance in this case has to account for the fact that it's a vector in two-dimensional space. So this is actually along the y-axis, and this is along the y-axis, except in the opposite direction, and this stays in the x-axis. So the overall voltage then, if I want to draw the magnitude in here, it's the square root of the components in the x-axis squared. So I have to take the x component. So in other words, this is Ri squared plus XL minus 1 over XC, oh, sorry, minus XC itself, because XC has a 1 over XC squared times I squared, and that is the overall voltage. So I already took care of the fact that I have a 90-degree angle in here by assuming that this is along the x-axis, and the difference between the two is along the y-axis, and this is the Pythagorean Theorem in this case, and the voltage in here is Ri, and the voltage in here is XL minus XC times I, and this is the actual voltage that I'm looking at from the power source. From here, we're going to find the same expression equals to V naught over square root of R squared plus XL minus XC squared. Obviously, for this simple case, it looks obvious. But if you have a more complicated circuit, you should proceed as in a similar fashion, okay? In a similar fashion, and that is basically how you handle AC circuit components. So in other words, you make the problem from being a time-dependent problem. By doing this trick, as basically you remove time completely, and you start dealing back with the circuit as if it's a DC circuit, okay? As if, it's not really. Because there is a phase shift in this situation, which is just the arctangent of this guy. The phase shift is the arctangent of the ratio of the y component, which is XL minus XC over R, okay? So this is in a nutshell how you handle your circuits, and this is how you take care of it. There is one question here which is very important, and that is the power. Okay. Once we answer the power, we're going to be in business, okay? Here is the deal, power. So we have a circuit that has some signal, okay? If, let's say, for example, the power source is V naught sine of omega t, it doesn't matter which one you write, sine or cosine at this point. So if this is the power, then we know that the current in the circuit will be shifted by an amount that is going to be phi in this case. So the current is going to be I naught times sine. Let's I use the I, but I'm going to use the maxes now, okay? So because I want to do something with the maxes. So there is a maximum value where the signal is oscillating both for the current. So this is I, not the big I. Then it's equal to I max times sine of omega prime t plus phi. Okay, it's shifted from the original one, basically by an angle phi. Obviously, the power that is being drained, power P, is still true in this case. It's the EMF times the current. And this is going to be equal to Vmax times Imax and times the sine of omega prime t times sine of omega prime t plus phi. Okay? Let me remind you of how Imax, this is actually the maximum current, and this is where the Vmax is. So it's the same current, same stuff. So Imax and Vmax are related to one another as Imax is equal to Vmax over the square over Z, whatever Z is. Okay? Z is being that complicated expression, and phi is the phase difference between the two. Okay? So what this expression look like then is the following. It looks like it's the power is equal to Vmax squared over Z times the sine of omega prime t sine of omega prime t plus phi. The power is time dependent, as you can clearly see. So if you plug in if you put, for example, your even a light bulb, it's going to drain energy at a constant rate. I mean, at a time-dependent rate. So you need to find the average power. So P average is the one that is actually of importance in here. The average power, so I'm going to call P bar, is equal to Vmax squared over Z times the average of this quantity. So I need to average this number. So I'm going to define the average. Here is how the average is defined. Okay. It's 1 over period, the integral from 0 to a period. Okay. That's it, of dt. So I'm going to multiply to divide by the period and sum through a whole period, basically. So if I do that, then I will have a sine omega prime t sine omega prime t plus phi, and I'm going to average this average quantity. The sine of an angle plus something, I need to be careful with it. This is sine of omega prime t cosine of phi plus cosine omega prime t sine phi. This is again, I don't need to do that. Times the sine of phi. This is the trig identity, okay? Another trig identity, that's sine of alpha plus beta is sine of alpha cosine of beta plus sine of beta cosine of alpha. So exactly what I've used in here, okay? So if I do that, I have a sine omega prime t times sine of omega prime t, that's a sine squared of omega prime t, and I have a cosine phi, that doesn't depend on t, so I'm gonna pull it out. And then I have a sine of omega prime t times a cosine of omega prime t times a sine of phi. So that too I need to integrate to find the sum. Okay, so the average power then is going to involve the 1 over t, the sum from 0 to t, which is a full period, times the first term. I have a cosine phi times sine squared. So I'm going to write cosine phi first because it's constant, times the sine squared of omega prime t dt, plus the second term. The second term will have a sine phi in it. So it's going to have, let's pull the sine phi completely. Okay, we don't need that inside the integral from 0 to t of a sine omega prime t cosine omega prime t dt. I'm going to argue that this number is 0. Okay, because I have a sine in here times cosine and there. I'm going to argue that this integral is 0, and let's see why that is. It should be obvious in here, because there is another identity from trig functions that sine of 2 alpha is equal to 2 times sine of alpha cosine of alpha. Okay, so I'm going to use that fact to rewrite this one as just 1/2 of the sine of twice the angle. So why did I say it's equal? That's a plus actually. So this is the first term, this is the second term. I'm going to deal with the second term first because I know it's going to be 0. So the second term will have 1 over 2 t and times sine of 2 phi in sine of phi in there, because the sine of phi is still a constant. The integral from 0 to t of sine of twice the argument, and twice the argument is this one. And the integral of a sine is a negative cosine. The integral of a sine is just a negative cosine. Don't forget to divide by this 2 omega prime. So it's going to be a negative sine of phi over 4t times omega prime times the integral from 0 to, it's already, we did the integral. So it's going to be a cosine of 2 omega prime t between 0 and t. Well, in the lower limit, it's 1. So it's -1 anyway, because t equal to 0, cosine of 0 is 1. In the upper limit, you're dealing with a cosine of 2 omega prime t. And that 2 is 1. Let's see why. Because omega prime t is 2 pi. Okay? And 2 pi times 2, that's 4 pi. Cosine of 4 pi is actually 1 also. So I have a 1 minus 1, and that is 0. So I don't have to worry about that. So the second term is completely 0, and that is because the average of the function that goes like this over a full period is going to be 0. Okay? Because sometimes it's positive, sometimes it's negative. It's going to cancel out on average. So I don't worry about this term. It's the sine squared that is always positive. That is going to be non-zero because it's always above the x-axis. So it's always going to be non-zero. So I'm going to take that, and that is actually the average power that I need to find. So the average power then is going to be a cosine phi that is going to come out of the integral times, I forgot about the other two terms in here. We forgot about the Vmax squared over z. We need the Vmax squared over z in here, okay? So we need that term in here. Vmax squared over z. And the integral, again, from 0 to t, there is another identity, trig identity. I know I have thrown a million trig identities for you guys today. The sine squared of alpha is equal to, actually, what is it? Or let me write it down as cosine of 2 alpha is equal to 1 minus 2 sine squared of alpha over 2, okay? In other words, I have a sine squared in here. All I have to do, sine squared of alpha. I have a sine squared in here. All I have to do is just basically move it to the other side, and it's going to be 1 minus cosine divided by 2. So it's going to be 1 minus cosine of twice the argument, which is 2 omega prime t divided by 2 dt. Well, this is 0. We just saw it, actually. It's the same thing as before. It's the same. Sorry, the integral of cosine is going to be a sine, and the sine is going to be, upper limit is going to be 0. So it's going to be sine of 2 omega prime t from 0 to t. The upper limit is going to be a sine of 4 pi, and the sine of 4 pi is 0, and the lower limit is going to be 0. So it's similar to the first case, except that instead of dealing with the integral in there of a sine to become a cosine, we're dealing with the integral of cosine to become a sine. And it's the same reason why that should be 0, because the sine function also is going to be periodic, and that is going to be 0 from the same reasons. The integral of 1/2, though, it's not 0. It's actually t over 2. So that is the whole work in here, just to get us to this point in here. It's Vmax squared over z times a cos phi times 1 over t times t over 2. And the t cancels the t. And that is very important cancellation, because we define the average in terms of the period. And now we don't want the period to appear in the whole thing. So the whole calculation yielded 1/2 really, and the cosine phi. So cosine phi plays a major role when it comes to power, okay? During the time when the circuit is actually in resonance, when phi, which is the arctangent of that angle, is equal to 0, at that point you have the maximum power consumption. Remember, phi, or tangent of phi, is equal to XL minus XC over R. So during when XL is equal to XC, namely the fact that omega prime is equal to omega naught, which is the resonance I mentioned before. this argument in here is 0, and the phi is actually going to be 0, and the whole circuit is in phase actually, okay? Phi is equal to 0 at resonance. And the cosine of 0 is going to be maxed. So the power will be at its max in there, okay? When the circuit is dominated by one or the other, then in this case, the phase can be pi over 2, in which case there is the least amount of consumption, okay? Whether we're in the extreme side when XL is very large compared to XC. So in this case, this number is actually going to be infinity. So in that case, the arctangent of infinity is pi over 2. Or in the opposite direction, XL over XC is less than XC. So it's going to be negative infinity, in which case the angle is going to be negative pi over 2. So in either case, the cosine will approach a very small value, okay? So that determines actually the power. So cosine pi plays a major role when it comes to power. Number one. Number two, this expression that I was dealing with, the sine squared in here, that I was trying to average and do this and that and use trig here and there, this whole thing has a name, and it's called the RMS. Because here is how what the power now boils down to. Let me write it down one more time. The power looks like Vmax squared, Vmax divided by Z times cosine of pi times another Vmax. So I'm going to write the Vmax in here, the second one. So I broke down that Vmax squared. Let's look at this Vmax times cosine squared so that we see exactly what we're talking about in here. This is the component. Where is my phasor? This is the cosine phi. It's this component, okay? Times Z. That is actually R. So in other words, this hypotenuse, which is actually Z times the Vmax in here, this is actually going to be times cosine phi. That is actually R. So the whole thing with the cosine phi included in it is going to be R times the current. But don't forget, I have a factor of 1/2 though, that we pulled from this whole integration in here. So we have a 1/2 in here. So in this case, this looks like it's actually the current I. So this looks like it's Vmax times Imax times 1/2. So instead of writing it this way, we're going to write it Vmax over square root of 2 times Imax over square root of 2, and use this expression instead, where this is going to be the effective voltage and this is the effective current. And this is what the power is now. Having it written it this way, it looks very similar to what we did in the RLC circuit, in the DC circuit, where we said the power in the DC circuit was equal to voltage times the current. End of the story. This looks very similar to it, but written in this form, not in this 1/2 form in here. So if I define my RMS, which is the root mean square, as being just that sine square, square the value and divide it by 2, then in this case you will end up with, square the value and integrate it and divide it by the period, then it's going to pull, each term will pull exactly 1/2 so that the expression looks like, so this is the AC circuit, it looks like the one from the DC circuit. That's why in the United States, the effective voltage, I'm looking, I have 1 minute, I know you guys what you are. So we have, in the United States, the RMS voltage is 120 volts. And that is actually the RMS voltage. So the Vmax in the United States, if I use this formula, is actually square root of 2 times 120 volt, which brings it to about 170 volt. So that is actually why the voltage in the United States maxes between 170 to negative 170. So when they give you 120 volt, they mean with it the root mean square. So this is the root mean square. Obviously, a lot of this thing sounds like a foreign language to you if you didn't speak any other foreign language to you, unless we do problems. So here is the deal. Come Wednesday, we're going to do applications from this chapter and basically get the power supply, get the RMS circuit, and we even at some point we're going to do an RLC circuit in parallel instead of doing it in series. And Hopefully it will make more sense for you guys. And then don't forget, we have a lab this coming Wednesday. So hopefully that's going to clarify more of these things, okay? Sounds like it's a good plan?
Sounds good.
Okay, very good. So I'm gonna stop sharing right now. Stop recording. And I will see you guys on Wednesday. Hopefully you're going to go through the textbook and probably see other things that I didn't mention in here. And we'll talk about it on Wednesday, okay?
Sounds good. See you Wednesday.
Wednesday. Let me stop recording first.